Welcome! Today we tackle a classic exam problem on digital modulation. Here is what we are given. An amplitude shift keying signal, ASK for short, drawn against a millisecond time axis from 0 to 8 milliseconds. The carrier is a sine wave at 1 kHz, written as sine of 2000 pi t. Our job is in 3 parts. First, find the digital information signal x of t that produced this ASK. Second, take that same x of t and redraw it as frequency shift keying. Third, redraw it again as phase shift keying. 3 modulations, 1 underlying message. Let us decode the ASK. The rule is simple. ASK turns the carrier on for a 1 and turns it off for a 0. So, we walk along the time axis 1 millisecond at a time and ask, do we see a sine cycle here, yes or no? Look at the first millisecond from 0 to 1. We see exactly 1 full cycle of sine. The carrier is on, so this bit is a 1. From 1 to 2, the line is flat. The carrier is off, so this bit is a 0. From 2 to 5, we see 3 full cycles, 3 milliseconds in a row of carrier on, so bits 3, 4, and 5 are all 1s. From 5 to 6, flat again, bit 6 is a 0. And from 6 to 8, 2 more full cycles. Bits 7 and 8 are both 1s. The bit pattern is 1 0 1 1 1 0 1 1, 8 bits in 8 milliseconds. The bit duration is exactly 1 millisecond, so the rate of x of t is 1 bit per millisecond, which equals 1 kilobit per second. This is the digital signal that the ASK is carrying. Now we draw FSK. FSK stands for frequency shift keying. Instead of switching the carrier on and off, we switch between 2 different frequencies. For our problem, the rule is a 1 is sent as sine of 2000 pi t, that is 1 kHz, 1 cycle per millisecond, and a 0 is sent as sine of 4000 pi t, that is 2 kHz, 2 cycles per millisecond. We just walk along x of t and pick the right tone for each bit. Bit 1 is a 1, so we draw 1 cycle of the slow tone. Bit 2 is a 0, so we draw 2 cycles of the fast tone. Bits 3, 4, 5 are 1s, so 3 cycles of the slow tone in a row. Bit 6 is a 0, so 2 cycles of fast. Bits 7 and 8 are 1s, so 2 more cycles of slow. Notice the visual signature. Where the bit is 0, the wave looks visibly tighter. Where the bit is 1, it looks more spaced out. The carrier never stops. The frequency is what carries the information. FSK is more robust against amplitude noise than ASK because the receiver only needs to recognize which of the 2 tones is present, not how strong it is. Finally, we draw PSK. PSK stands for phase shift keying. Now we keep the frequency fixed and switch the phase. For this problem, a 1 is sent as sine of 2000 pi t, and a 0 is sent as cosine of 2000 pi t. Cosine is just sine shifted by 90 degrees, or 1/4 of a cycle. So when the bit is 0, the wave starts at its maximum value instead of starting at 0. We walk along x of t and pick the right wave for each bit. Bit 1 is a 1, sine. Bit 2 is a 0, cosine. Bits 3, 4, 5 are 1s, sine again, for 3 milliseconds. Bit 6 is a 0, cosine. Bits 7 and 8 are 1s, sine, for 2 more milliseconds. The visual signature of PSK is the abrupt break at every bit boundary where the phase changes. The number of cycles per millisecond stays constant at 1, but at each transition between 0 and 1 or 1 and 0, the wave jumps. PSK uses the same bandwidth as the original carrier, which is why it is bandwidth efficient. The price is that the receiver needs to know the carrier phase precisely to decode it. Let us summarize. We started with one digital signal, 8 bits long, the pattern 10111011. We sent the same information 3 different ways. ASK changes the amplitude, carrier on for a 1, off for a 0. FSK changes the frequency, slow tone for a 1, fast tone for a 0. PSK changes the phase, sine for a 1, cosine for a 0. All 3 carry the same 1 kilobit per second of data. The differences show up in noise tolerance, bandwidth use, and receiver complexity. ASK is the simplest but the most fragile. FSK is the most robust but uses extra bandwidth. PSK is the most efficient but needs careful phase recovery at the receiver. That is the foundation. In the next video, we will run the same 3 keying schemes at a microsecond timescale.